Monday?
No, this is new. This is new stuff. What we're going to look at today, we're going to look at this section 390 in the book. It's called differential, linear approximations or differentials, whatever you want to call it, either or. Okay, and what we're doing here, the concept is really simple. We've got some function, and we are going to use a tangent line as an approximation of the function. Now, that's obviously not going to work well everywhere. As you start to move far away from the point of tangency, you can see that the blue tangent line and the black curve start to deviate to the point where the blue line is no longer a very good approximation. But if you stay close to home and the curve isn't extremely curvy, then yeah, it's not bad. Okay, so that's the idea. That's just a linear model. That's no big deal. I mean, that's something that we have a little bit even talked about in the past. But what we're going to look at today is a way that we can exploit this linear model to make real quick estimates using calculus of how much a function changes over an interval. Okay, on a certain change in x, what can we approximate as being the change in the value of the function? So, but to get our bearings here, let's just explore this picture a little bit. So we've got a point of tangency, and the point of tangency here, this is something that is known. It's a known value of the function. Maybe it's a convenient point. Okay, and then we're gonna look at what happens around that convenient point where we know the value of the function. So if we call this value x and this function is f, then the coordinates of that point are, of course, just x, f of x. There's the ordered pair. So what's going to happen then if we move away from that point by some known amount? Let's say that we're going to walk away from the point of tangency by an x value, delta x. Okay? So if I do that, let's say we're going to walk in the positive direction arbitrarily. It doesn't really matter. So if we walk in the positive direction, that's going to put us at a new x value, which is x plus delta x, whatever that delta x might be. That point on the curve then would have the values. The x value would now be x plus delta x, and the y value would be f of x plus delta x. Okay, if we want to find the actual change in the function, well, the actual change in the function from our starting point to our ending point, right? We started here and we moved delta x to the right. The change in the function we might call delta y. Okay? And that would just be the difference in those y coordinates, wouldn't it? Right? It would be this y value, so f of x plus delta x, minus this y value, so minus f of x. Okay? No big deal. That's the exact change in the function. Yes, sir?
So we're just using the linear function to try to fit it.
Well, yeah, it'll make a lot more sense here in just a little bit. What we're going to do, I want to get the picture. I want you to digest the picture a little bit, and then we'll talk about, well, I mean, how is this calculus? What are we doing here that's calculus in any way? If we look along this line right here, if we scoot over delta x to the right, well, the line has risen by a different amount. We might call that dy. Okay? Different than delta y. Delta is like a capital D, right? And what's that change in y going to be? If we were to look a little more closely at this right triangle down here, we could see. Right, there's a right triangle, and we know that the base of that right triangle is delta x, or we might call it dx. Okay, same thing. And the height is dy, but if we knew the slope of that line, isn't slope just equal to rise over run?
Yeah.
Right? So this could be a slope triangle, right? We could say that the slope of the tangent line just equals dy over dx or delta x, whichever one we want to call it. And if we were to solve that for dy, which is what we're really trying to find an expression for then, dy just becomes the slope of the tangent line times dx, right? Okay, now here's where the calculus comes in. What is the slope of the tangent line? If this function is f, and the value of x right there is, we're calling it x, then what's the slope of the tangent line equal to? How do we, I mean, in calculus, what's our, yeah, the derivative, right? The slope of the tangent line would just be the same thing as saying the derivative of f of x, or f prime of x, we could call it, right? Okay, so we get a better expression for this then. What we can say instead is that dy is equal to f prime of x times dx. Okay? So there's a calculus expression for us that is equal to the change in the value of the line. The change in the value of the function is going to be a little bit different, of course. But for small values of delta x or dx, whatever we want to call this distance, when we're close to home, they're going to be roughly the same. It's a good approximation, and that's what this section is all about, is making differential approximations. Yes, sir?
So how do you know that line has the same slope as the derivative line?
Because this is the derivative line. It's by definition a tangent line.
Well, what if there was one tangent to that other point? Would that also be?
So, say it again. If there's this point right here,
Yeah.
well, that would be a different tangent line, right?
Yeah, so that would be the derivative of the function.
You're right. You're right. But all we're trying to do now, we're not trying to get an exact answer. Let me try to restate the question here a little bit. The question is, how do we know that this blue line is the same as the derivative line? Well, the derivative line depends on what your point of tangency is. We're locating this at our convenient point. That's kind of our anchor point, right? That's where we started the whole business. We know that the point of tangency and the curve exactly coincide at that one point. So as delta x or dx shrinks down to 0, the blue line and the black curve come together, and they are exactly superimposed at that one point, right? As we move away from x in either direction, presumably if this curve isn't linear, which this one isn't, then the black curve and the blue line are going to start to diverge. Okay? The blue line, once again, is just it's the tangent line at this point of tangency, at the point of tangency defined as x, f of x, right? So that's what we're using based on this one value that we know. We know the value of the function there. It's maybe a convenient point for us. And we'll see some examples where that terminology, I think, will make more sense. Based on this one point, the tangent to the curve at that one point is an okay approximation as long as we stay close to home, maybe even a good approximation. But only if we stay in this region in here. Once we start to get out of that region, they start to diverge to the point where maybe it's not a good approximation anymore. Okay? This is an approximation here. This is something different than what we've done in the past. We're not trying to get an exact answer. We're just trying to get a quick way of approximating how much the curve has changed. How much has it risen or fallen over some change in x, right? And so all we're saying here is that the actual amount that the curve has changed, delta y, is approximately equal to dy. Okay? So this is, if there's one big equation that summarizes everything in this section, this is it. Delta y is roughly equal to dy, which is simply the derivative times dx. Okay? That's our differential approximation for the amount that the function has actually changed. Okay, now why would we do this stuff? Well, here's an example of why this might be important. What if we wanted to look at, how about if I do this? Let's see. Okay, what if what we're trying to do here, let's say we take an example where we're calculating a volume of a sphere. So we're going to take a ball bearing. The radius of a ball bearing, R equals 0.7 inches plus or minus 0.01. Okay, so what would we call that, plus or minus, you suppose? How come that's there? This is a real-world problem here. We're measuring a ball bearing.
Error?
Yeah, it's measurement error, right? We have to have a little tolerance there because we can't measure it perfectly. Whatever the instrument is that we're measuring this, it's probably a caliper or something. Well, there's a little bit of uncertainty in that. We can't read it exactly, and it's mechanical, and so maybe there's, it's not perfect. So there's a little bit of measurement error associated with that. Now, if I want to calculate the volume of the ball bearing, what's the formula we use to calculate the volume of a sphere? A known radius. What is it again? No, that's surface area. What's volume? 4/3 pi r cubed. Yeah. So volume is 4/3 pi r cubed. So if I calculate the volume of this ball bearing, I can plug in 0.7 inches, and I'm going to get some answer out of this. Okay, but what's the problem with my answer? Maybe not a problem, but what's the reality of my answer?
It'll be a huge decimal number.
It's going to be a huge decimal number. Is it going to be exact?
No.
No, it's not, because the measurement of the radius was inexact, right? And so what we say in math is, or in science, we're going to propagate that error. That error enters into our calculation when we plug in a value for R. And so we're going to get back some number. What is the number? We'll just see what we get here. So if we plug this in, okay, we get I could keep going, and we'll talk about how far I really need to go here in a little bit. But I get that many cubic inches. However, there's going to be a little bit of a deviation here. How could I calculate the upper limit of what's the biggest volume that it might possibly have if I know accurately the amount of uncertainty in the measurement? Okay, sure. Everybody see that? I could jump this up to 0.071 because that's how far off I could be in the positive direction, right? And I could do the same calculation and get a slightly bigger decimal, and that would be the upper limit of volume. Agreed? Or I could drop it down from 0.7 to 0.69, and that's going to give me the lower limit of volume, right? And then that's going to give me the range of possible volumes that we have. We don't know exactly what it is, but it's someplace on that interval. Agreed? Okay, that's a little bit clumsy to do, though. If the calculation is a big one, to go through and have to perform the calculation goes twice around the original calculation is a little bit clumsy. We don't like to have to do that. We'd like to be able to just say, okay, roughly, fairly accurately, how far plus or minus is the volume going to be off? Let me ask you this about if we had done that, and I won't even take the time to do it, but I want you to make a prediction for me. If I had plugged in 0.71, made the calculation, plugged in 0.69 and made the calculation, do you think that the amount that we were off from the volume that we calculated at 0.7 would deviate equally above and below?
No, because that's
no, you're right, it wouldn't, because it's a cubic function, right? And so if I move from this point, we can kind of see this graphically here a little bit. If this is, this is 0.7 on the graph. So if I move forward a little bit, if I want to move up a little bit to the right, the amount that the blue curve increases is not going to be the same amount that it decreases if I move to the left by that amount, because the curve's slope is changing, right? So there's another disadvantage to this, to making an exact calculation of what are the limits of our volume calculation. It's a little bit awkward, not only because we have to do that calculation repeatedly, but also because the upper limit is going to be a little bit further off in this case than the lower limit. They're not going to be equal. It's not symmetrical, right? Wouldn't it be nicer to just be able to say the volume is some number plus or minus something, right? We'd like to have a tolerance in there that's symmetrical about whatever our calculation is, okay? Now let me ask you the same question again about the blue line. If we go back to this example here, the curve is going to change by different amounts if I move to the right or the left by delta x, right? But the line, what about the line? If I move to the right by a certain amount or the left by a certain amount, it's going to be the same because it's a line, right? It is symmetrical about that center point, right? Okay? And the symmetry, you could even see the symmetry as rotational symmetry. I mean, this is going to hurt your brain a little bit, but think about this. If I were to put a pin in there and I spin the black curve around, it's not going to line up, is it? Right? It's going to be, there isn't rotational symmetry about that point, but the blue line there is, right? It's going to have rotational symmetry about that point. And so we like symmetry when we're doing these things. I mean, that's nice to have. So here's where the calculus comes in then. When we make this differential approximation, it's easy to do, okay, and it has the benefit of being symmetrical about the calculation. So let's go back to the volume, and let's apply this to the volume situation. Back up just a little bit here. There. Okay, so there's our volume formula. Let's come down here, do a little work down here. So if volume equals 4/3 pi r cubed, right? Then we want to find out what dV is, right? Isn't dV just going to equal v prime times dr, right? If in the last page we said that dy equals f prime of x dx, in this new example, instead of y's, we've got v's, right? And instead of x's, we've got r's. And instead of an f, we have a v, right? Okay, it's a volume function, okay? Now, I want you to notice something else here. What if I just wrote, I started off with this equation. Here's a super easy way to remember this. That's one way to write a derivative, isn't it? That's what we call the quotient form of a derivative, okay? Here's another way of writing the same derivative, f prime of x. If I just solve for dy in this equation, look what I end up with. I end up with an expression for the differential. And by the way, that's what we call the differential. Is that dy by itself. The approximate change in the value of the function, the y value. Okay, so if we go back here to the volume example, if we just wrote this as dV dr equals what? What is the derivative of volume with respect to r? By the power rule. Okay, question? Okay, hold on just one second. Answer this first, and I'll take your question. What's the derivative of this function with respect to r? Okay, good. I bring the 3 out front. 3 times 4/3 is just 4. 4 pi r squared. Okay.
Oh, that's the surface.
It just accidentally is the surface area. That's one of the hidden super cool symmetries about a sphere, is that the derivative of volume is equal to that, which is really amazing that it's that way. Once you look at it a lot, you kind of think, well, it kind of has to be that way, but it's just weird that it is. I mean, spheres. That's why yet another reason why they're so symmetrical. Only for spheres, yeah. Okay, so hang on one sec. So then if I want to solve for dV, if I want to find the approximate change in volume that we're going to get, then I just multiply both sides through by dr, right? And I end up with my answer, dV equals 4 pi r squared dr. This is, by the way, we wouldn't even have to talk about differentials as an approximation. And this is what we call the differential form of a derivative in just calculus. All those derivative forms that you guys have learned can be rewritten as differential forms by just multiplying both sides by dx. For example, I don't want to get too far off track. I'll give you one quick example. If we took the derivative with respect to x of sine x, right? Whoops, hang on a second. I'll do it this way. Messed up. The derivative with respect to x of sine x just equals cosine x, right? So if I multiply both sides through by dx, I get the derivative of sine x equals cosine x dx. That's just the differential form of the derivative of sine x. Nothing, mysterious or complicated about it. We just are, instead of writing it as a derivative with respect to x, we're just writing it as a derivative, just a piece of something. Okay? That may not seem like much now, and it's not. Algebraically, it's just as simple as multiplying both sides by dx. But that plays a huge role in what we're going to talk about in about a week for the rest of the year. Yep. Well, dx is just, we're asking the question, what's the rate of change of sine x? We want to know how much is sine x changing for an infinitesimally small change in x. That's all the derivative function is saying. By asking what the slope is, that's it. It wants to know what's the change in the y value of this function, sine x, when I make a small change horizontally in x.
So what is dx x
So dx is, it's not really x prime. It's just an incremental horizontal change. dy is just an incremental vertical change. And so dy dx is just really, when I say something like dy dx, that's really literally just rise over run. That's why it's a slope.
For the last page that we were at,
Mm-hmm.
when you made it dx and dy that arbitrary to the line.
You mean this page right here?
Yeah.
That one?
Yeah.
No. So I made it that way on purpose because dx means a horizontal change.
Yeah, but it's not changing the constant.
What's a constant?
Dx. Because it's not like dy where there's two values and then the dy is just a change in value.
No, it is. What's x plus delta x minus x? Yeah. Or dx, whatever you want to
Why
call
would
it.
you subtract x?
Well, because it's the change in the x coordinate. It's the change in the x value is this x coordinate minus that x coordinate. Okay? So it really is a difference. Yeah. Okay, so then if we go back to this. Okay, so we end up with this differential approximation. Now, what does it mean? How is that helpful in this situation? Well, here it is. dV is, let me go to the next page. I'm going to take this thing, we'll go to the next page, and we'll attach some numbers to it. Okay, so this is just the approximate change in volume, right? What's R, you suppose? If we look back at our problem, there's our problem. What's R? 0.7, right? That's the measured value of the radius, okay? then what is DR? $1 million question.
Is that the error?
Yeah, that's the measurement error, right? That's the amount, and it makes sense, doesn't it? That's the amount up here, we call it the dx. It's the amount that we might be off from our known value, or the convenient value, right? It's the amount that the independent variable was x in this case, now it's r. That's the amount that it might deviate from the point of tangency, right? So dr is just this, right? 0.01. Okay. Well, you're right, it is. It's going to be symmetrical about both sides, right? So dr equals plus or minus 0.01. Okay, and look what we get when we plug all that stuff in. If I plug the numbers in, I get dV equals 4 times pi times 0.7 squared times plus or minus 0.01. Now, if I put all that in my calculator, I'm just going to get an answer. That times, I get plus or minus 0.0143, etc. Blah, blah, blah. Okay, so what is that? Yeah, that's the amount that the error propagated in my volume calculation. So my volume might be off by as much as plus or minus 0.01437, and I think we were measuring in inches, right? So cubic inches. Whatever my volume calculation is, this is how far off it might be.
But so
it's going to be different from bottom and top.
You're right, but this is my linear approximation. This isn't exact, right?
Oh, okay.
This is the linear approximation. It's going to be off a little bit. It's not perfect.
So why can't you just take the difference when you plug in the error and then just say it's the same for up and down since it's just approximation?
Well, you could. Your suggestion is, why didn't I measure maybe?
Why don't you plug in 0.0, like 0.71,
Mhm.
and then you just find out the deviation in the original, and just say, okay, it's that much deviation up.
Up or down?
Yeah.
Okay, because, well, first of all, because it's inconvenient to make that calculation again. And the other thing is because what if one side is significantly more extreme than the other, like in this case? Then I might be saying, okay, we're going to move clear up to here and down to there, right? And so that's not conservative. That may be outside the actual change in volume, right? If I average the two, which is what I'm doing if I use a linear approximation, notice that on the right side, the blue ends up being bigger than the red. On the left side, the red ends up being further away than the blue, right? So the line changes by more to the left, but the curve changes by more to the right. So the linear approximation is going to average out the two extremes, right? And it's going to give you kind of a middle ground approximation on both sides. So it really is better. You could do it that way, but A, it's more inconvenient, and B, it's not as good in the sense that it's not as accurate.
Wait, so when you say average, so that means it's like, it's below the highest, but above the lowest?
Right. Or vice versa. It could be.
Chapter 6 already.
Absolutely.
Well, oh, I want
He
to
wants
ask
two.
Teacher, thank you. Thank you. All right. It must be a Pi Day thing, right? Okay, so, right, so do you see what I'm saying?
Yeah, I can't concentrate with that strawberries.
Honestly, are you gonna eat that?
Not now.
Well.
No.
Okay.
Go away.
I got a
Go
whole
away.
cake. I got a whole cake, right here.
Okay, and so look, you get a whole cake for a strawberry?
I'll trade it. Straight
Are you
up.
serious?
Straight
That's
up.
not a good trade.
Also, for me it is. I love strawberries.
Okay, talk to me after class. We'll do the horse trade now. Okay, so okay, so you get the idea. Now that's a lot of theory. It's not that bad though. Let's try a problem. I'm gonna make up another one here. Try this. Knock this one out. It's no big deal. Let's say we've got a cube. Okay, and we want to find let's say we want to find the volume of the cube, and we can measure x to x equals 10.1 centimeters plus or minus 0.1 centimeters. Okay? Okay, I want you to, let's find out what is the propagated error in calculating the volume of that cube. Yeah.
But like for the last question when you found the average deviation,
Mhm.
would that be like not very practical because if you're actually like designing stuff or like designing like a thing,
Mhm.
and you say, okay, here's the average deviation, and then like it's like way bigger than or like
It's going to be right. It's going to be in the middle, right? Exactly. And so, what we would do, where this would come into play, would be like in engineering. In engineering, if we were designing ball bearings, we'd say, okay, we need that. We'd probably work backwards and say the volume has to be. Let's say that how are we going to do this? Well, let's just work it this way. Let's say that these, because of the mass of the ball bearings, the volume is going to be proportional to mass, and so the volume has to have a certain tolerance, or when this thing spins around really fast, it's going to throw it off center. It's going to wobble. Yeah, go ahead. Right? So you see where I'm coming from on this. So then we want to make a quick calculation that says, okay, well, what can the error in radius be so that our volume is within the tolerances? Now, we're always going to have a safety factor in there. We're going to make a calculation and then say, okay, now it has to only be, let's say, 60% of that value. We're going to move it in even a little more tightly because we want to be conservative rather than, right? Okay. I understand where you're coming from, but this is really the way you do it. This is a quick way to make an approximation. You'll see some examples here where it's obviously useful. I promise you. Okay, so let's try this one then. We're calculating volume. What's the formula for the volume of cube? Which is x cubed. Okay, so if we want to calculate then, look how easy this is. If we want to calculate the approximate propagated error in volume, it's just dV. What's dV?
2x.
Well, it's 3x squared dx. I just tacked the dx over here instead of down there, right? Now let's plug in those numbers, and look how easy it is. It's just 3 times 10.1 squared times plus or minus 0.1. Somebody throw that in your calculator for me, and what do we get? Negative plus or minus.
No, that's not right.
It's 30.6.
30.60. Okay. So out to 3 places, we'll say 30.6 plus or minus 30.6 cubic centimeters. That's how much volume, how much we could be off approximately in our volume calculation. Okay. We didn't even calculate what the volume was. We could. The volume is just, well, okay, but now there's the next point. So that's a very good question. Is that a lot or isn't it?
It is.
Depends. 10.1 cubed is what? 1,030.
Oh, relative. Everything kills me.
Exactly. So the actual volume we calculated was 1,030 cubic centimeters. So being off plus or minus 30.6, is that a big deal or not? Even there, it's hard to tell. But there's a real simple way to tell. I couldn't have scripted it better. That's exactly what I hoped somebody'd ask is. Seems like a lot, right? No, I didn't script it. But we can calculate, instead of just calculating dV, which is important, what we really want to do is we want to calculate the relative propagated error, right? And the relative error is just going to be the differential approximation. So how much is the quantity changing divided by the actual value of the quantity, right? So in this case, it would have been plus or minus 30.6 divided by 1,030. Okay, but watch this. It even gets better. You don't even have to do you don't even have to do all those calculations, because if we were just looking for the relative error, which is what we would have been doing in a real world situation, we'd want to know how much, as a percentage, how much is the volume going to be off? Well, dV, we already calculated up here, dV was 3x squared dx. We know that v is x cubed. Algebraically, what can we do there? Yeah, exactly. We can cancel an x squared, top and bottom. So I end up with 3 dx over x. So that's our expression for relative error. So if I want to calculate a relative error, then dV over v is just 3 times plus or minus 0.1 over 10.1. Now, notice the units would go away here. I would have, if I kept the units, I would have had centimeters and centimeters, and they would have canceled. This is unitless, which is beautiful. That's what we like in physics, is a unitless quantity, because it's scalable. Okay. Now, if I multiply this, what do I get if I do this? 3 times 0.1 divided by 10.1 is what? Somebody? 0.0297. Okay, if I write that as a percentage, which is even better, that's plus or minus 2.97%. Now that means something. That means something. That means that the volume is going to be off. Our volume calculation could be off by as much as roughly 3%. Okay, and so that's, now that might be good enough and it might not be, but we're going to have some idea of whether or not it is good enough. We know what our tolerances need to be, right, in an engineering situation, for example, right? On that last situation we looked at, on those volumes for those ball bearings, was that any good? We don't know. We never found out. All we knew was that this is how far off the volume calculation could be, but we want a percent instead. So what could we have done here instead? If we want to calculate the propagated error in volume, we really want the relative propagated error, right? So we should have calculated dV over V. Now dV was just 4 pi r squared dr. And V was 4/3 pi r cubed, right? So I can do some fancy stuff there. The pi's cancel and r squared cancels. And 4 divided by 4/3 is same as 4 times 3/4. So isn't that just 3 dr over r? 4/3 times 3/4, right? And so we get 3 times plus or minus 0.01 over 0.7. What's that?
0.0428 or 4.9.
0.0429. So plus or minus. So if I move the decimal 2 places, that's about plus or minus 4.29%. Right? Make sense? So we can do that, that's not hard to do. Okay, what if we wanted to say something like this? Now, what if we want to say,
Is this optimization?
we're about to, I better stop. What's that?
Is this optimization?
No, this is differential approximations, linear approximations. Yeah, the test you guys are going to take next week, I'm just going to call it applications of differentiation. So what it's going to be is optimization mainly, but also this. A little bit of both. We'll mix and match.
Are you going to